Swayam Prabha. Digital India. Educated India.
So, welcome to the second lecture of Module 6. In this lecture today, we shall continue our discussion on powder feed based additive manufacturing system. So, this is going to be the content for the second lecture. We shall first discuss about the powder feed additive manufacturing process modeling. We shall discuss about the process parameters influencing the powder feed additive manufacturing, the catchment efficiency, stream characteristic, particularly the powder stream characteristic, bead profile, and then we shall discuss some of the major application of powder feed additive manufacturing, such as its application in realizing the large scale additive manufacturing parts, its capability of realizing the functionally graded materials, its capability of repairing or restoring the features, and of course its conventional capability, that is surface cladding. And also we shall discuss one of its nowadays emerging application, that is called as grid stiffened structures. So the process parameters affecting the powder feed additive manufacturing are broadly classified into four categories: the parameters related to the laser, the parameters related to the feeding, the parameters related to material and design, and the parameters related to motion and path. So the parameters those are associated with laser are like the power of laser, the diameter of the beam, the beam profile. Beam profile means the intensity profile, whether it is TEM00, the transverse electromagnetic mode, and then the working distance. Working distance is nothing but the distance in which we assume that the laser is workable. The diameter changes from capital D, then its minimum diameter to small d, and then to capital D. So this is called as working distance. Also the wavelength of the laser which we are using, because most of the time we are going to deal with metal, therefore 1 micron wavelength is preferable. Then the parameters related to the feeding of the powder. In that case, what type of nozzles we are using. We have seen in our last lecture the different types of nozzles which can be used to feed the material into the molten pool. Then the flow rate of the powder and the gas flow rate, and we have also seen in most of the additive manufacturing system a coaxial nozzle is used which utilizes mainly 3 ports for the gas flow: one to protect the optics, second to carry the powder, and third to protect the molten pool from the atmospheric gases. So the flow rate of these gases is another very important parameter for powder feed based additive manufacturing system. Then the parameters related to material and design: the material of the powder itself, diameter, distribution of the powder particles, shape of the powder particles, material of the substrate on which we are depositing, heat treatment of the substrate, geometry of the substrate, and the geometry of the deposited region. Let me explain to you these two important things. The first one is the geometry of the substrate, because sometimes we may deposit on a flat surface. Sometimes it may be possible that the substrate itself is curved like this, and in that case you can see the geometry of the substrate is changing, and hence therefore I have to maintain the parameters also in such a way that I will be able to maintain the particular distance between the nozzle and the substrate while depositing the new layer. And then another parameter is geometry of the deposited region. So for example, you are realizing any overhanging feature, then that will be another consideration, because in that case also you have to either tilt the table in such a way that your gun become perpendicular to the plane of deposition, or we tilt the gun. Then the next is the motion and path. By what speed you are scanning while depositing the material on a substrate, that is called as scan speed. What is the overlap between the two subsequent deposition tracks? What is the path of the deposition? Interlayer dwell time. After depositing of each layer, how much time you are waiting to cool down the layer? And in some cases, if you are dealing with such hard materials, preheating is also required. So before depositing the next layer, we need to preheat the pre-built layer or the substrate in such a way that we reach to a certain amount of temperature and then we deposit the next layer. So this is the overall picture of the process parameters influencing the powder feed additive manufacturing. Now let us discuss about a very important phenomena. As you know that the laser cladding is the build process in powder feed additive manufacturing. Therefore, let us discuss a little bit more about this particular technique. So laser cladding, where it was invented, I have already mentioned this, was something like this. It was shown by Professor William Steen, where I have already mentioned there is a CO2 laser coming from here, high power CO2 laser, creating a molten pool, and from the side we are feeding the powder into the molten pool. But soon after that, the system was converted by Professor William Steen in such a way where there was a conical nozzle and the powder was flowing through this annular nozzle and the laser was coming at the center, and this was creating the molten pool, and the powder was fed in a conical way surrounding it. There were of course two reasons for that. One, to obtain the omnidirectionality, and another is to obtain the better catchment efficiency. So let us first talk about what is this catchment efficiency and how can I calculate the catchment efficiency for a very simple laser cladding operation which is using a side feeding nozzle. So the catchment efficiency eta can be given as the mass of the clad layer divided by the mass of the powder ejected from the nozzle into 100. So by experimentally we can easily do that. We know the mass flow rate which we are supplying through our feeder or the metering unit which we have discussed in our last lecture, and by measuring the amount of the deposited layer on the substrate after a run maybe of L length, and then we can divide and easily we can calculate the efficiency or the catchment efficiency of the process in the experimental manner. But now let us assume a very simple case of side feeding. In the case of side feeding nozzle, we used to have a laser which is coming at the center like this, and there is a powder stream here. Assume that this powder stream nozzle is tilted at an angle theta from vertical. Now for this very simple case we can find out the catchment efficiency very easily, but please remember that this whole calculation will be only valid for the side feeding nozzles, and that will be just to give you an idea that how much these processes are efficient for the catchment efficiency. So first of all, so to find out the catchment efficiency, it will depend on two things. First is the size of the molten pool which is created on the substrate and shown here in the red color on the top view. So this is the top view of the same, and here this red color spot is showing the molten pool diameter, because whatever powder particles are falling onto the substrate will get stick to the substrate only in the region where the molten pool is there. I mean the temperature of the substrate is above the melting point of the powder. Then the second is what is the amount of powder totally striking on the substrate. So as this powder stream tube, which is of maybe assumed to be of diameter dp, is striking the substrate, will no longer having a projection on the substrate in circular cross section. Instead, the projection of this or the cross section of this particular tube on the substrate will be elliptical. That is obvious. Now our aim will be to find out these two areas, the area of the molten pool that I am writing as AM, and the area of this powder stream striking on the substrate, and that I am writing as AP. So of course, to find out AP, I already know dP. So to find out AP, it will be very easy for me. AP will be equals to the length of the minor axis B into the length of the major axis C into pi by 4. So here we can easily find out the value of B, because B is going to be same as dP. Fine. So dP is same as B. So diameter of nozzle will be equals to the minor axis of this projection, but the major axis C will be different and it will depend on the angle theta. So now let us assume that if I draw a perpendicular from this point to here, the length of this perpendicular will be dP, and if the nozzle making theta angle from vertical, then of course the perpendicular of this nozzle will make theta angle with horizontal as well. So that is why this angle will be also theta. So now I can easily find out this length. This length, which is nothing but C, and this C will be equals to dP divided by cos theta, if I consider this right angle triangle, this one. Hence, once I know the value of C, I can easily find out the area. AP will be equals to pi dP square by 4 cos theta. It is obvious from here, if my angle theta is 0, the area of the powder stream projected on the substrate will be pi dP square by 4, which is nothing but the circular cross section. But if this theta is 90 degree, meaning to say it is almost horizontally we are supplying the powder, then powder will be everywhere, right? So the area will be infinity. Now let us try to find out approximately the size of this molten pool. So this can be done very easily by the Rosenthal's equation for a moving point heat source. Of course, we are considering here the point heat source. You may further refine the model by considering the surface heat source or the volumetric heat source. And if it is a point heat source, by the Rosenthal equation, it says, so if it is a moving point heat source, the Rosenthal equation says T minus T naught will be equals to P naught divided by 4 pi K exponential minus V zeta by 2 alpha into exponential minus VR by 2 alpha, where T is the temperature anywhere at a distance R in the molten pool, T naught is the ambient temperature, alpha is the thermal diffusivity, V is the travel speed, xi is nothing but x minus Vt, and it is the distance along the travel direction in which you are moving your laser beam. For example, you are moving in this direction, so xi will be nothing but measured in this direction. So if this is my coordinate x and this is my fixed coordinate y, then I am assuming a coordinate system on the moving spot of the beam, and that I am writing as xi here. So of course the position of this xi will be equals to x minus Vt. So the value of this xi will be equals to x minus Vt, and the r is the radius of the melt pool, P naught is the absorbed power, and K is the thermal conductivity. Now in the moving coordinate system, which is at the tip of the molten pool, because xi is corresponding to the moving coordinate system and I am considering just at the tip, hence the value of xi at this location will be equals to 0, meaning to say at the tip of the beam. Therefore the temperature profile, if I consider about this particular point, will be equals to T minus T naught P naught divided by 4 pi K exponential minus VR by 2 alpha. So this is the temperature distribution. Of course we are considering that we are sitting on top of it, right? Like we are considering in the moving coordinate system. Now to obtain the proportion where the temperature will be more than the melting temperature, we have to solve this equation for T equals to Tm, meaning to say we are trying to find out the boundary of this or the value of this R where the temperature will be greater than Tm. So let us put T equals to Tm in this equation, and finally you will have this expression. Now of course from this equation we can easily find out the value of R, but let us further simplify it. Of course this equation itself is quite simplified and you can use it directly to find out this radius of the zone. Inside that the temperature is greater than the melting temperature, but let us further simplify it. And I am trying to do the Taylor expansion for this particular expansion. We know that e to the power minus x about 0 can be written as 1 minus x plus x square by 2 factorial and so on. So let me neglect all the terms coming here, all the terms except the 1. In that case, if I consider this to be 1 approximately, then if I put this expression also on the left side, then this whole term will be equals to 1, and as a result approximately the radius of this melt pool will be equals to P naught divided by 4 pi k into Tm minus T naught. So this is an approximation to find out the radius of the melt pool. Now assume that there is a uniform intensity distribution of the beam projected. So this is the beam coming and we are assuming that it is having a uniform distribution of the intensity. Therefore, the area of the beam on the substrate will be equals to pi r square. Hence, it will be P naught square divided by 16 pi k square Tm minus T naught whole square. Now I have got the area of the molten pool and I have got the area of the projected powder stream also on the substrate, and hence I can now find out easily the catchment efficiency. So catchment efficiency eta for this simple case will be the area of the molten pool divided by the area or the projected area of the stream on the substrate into 100. Further, after simplifying it, I will get this expression, and from here, as I have considered several assumptions, let me consider that on what parameters actually the eta is proportional. That will be more appropriate. So for the comparative study, of course this catchment efficiency formula will work, but if you want to absolutely calculate this value of eta, it may deviate because of our lot of assumptions, such as considering the point heat source, considering the Taylor expansion for the expression coming there, and that too with neglecting the higher order terms. So here you can see the catchment efficiency is directly proportional to P naught square cos theta divided by dP square k square into Tm minus T naught whole square. So this is how you can find out the catchment efficiency of a side feeding nozzle in the laser cladding process. Now let us consider a few examples. In the first example, in a powder feed based additive manufacturing process, an off axis nozzle is used to feed the material into the molten pool. If with the same setup and the laser power, the material is changed from material A to B. It is also given that if the melting point of the material A and B are same, but the thermal conductivity of material B is 4 times higher than the thermal conductivity of material A, then find out the ratio of the catchment efficiency for both the materials. So in summary, it is saying that the thermal conductivity of material B is 4 times the thermal conductivity of material A, and rest of the parameters are same. It is very much similar like if we are considering copper and steel. Of course, there is a melting point difference, but the conductivity is around 8 times higher than the steel. So it is very much similar case to that. So let us see what happened if our substrate is showing a very high conductivity. So in that case, if I just recall my formula of the catchment efficiency and I took the ratio of the catchment efficiency for material A and material B, as other parameters are same, there will be a ratio of KB square divided by KA square. We know that KB is equals to 4KA, and therefore eta A divided by eta B will be equals to 16. In other words, I can say the catchment efficiency for material A will be equals to 16 times higher than the catchment efficiency of material B. Therefore, more conductive the material is, less will be the catchment efficiency, and this is because the size of molten pool will be very small in those cases, and that is why in the case of the materials such as aluminium, copper, where the conductivity is very higher and reflectivity is also very high, the size of the molten pool is very small, and by keeping the same process parameters, if you run the setup, you will end up having very bad catchment efficiency. Another example, in a powder feed additive manufacturing system, the steel metal powder is injected using an off-axis nozzle at an angle of 60 degree from vertical through a nozzle of diameter 5 mm. If the laser power is 1 kilowatt, find out the catchment efficiency of the process. So it is very straightforward question. It is also given to you that melting point of the steel is 1425 degrees centigrade. The ambient temperature is 25 degrees centigrade. Thermal conductivity is 50 watt per meter Kelvin. So we know the formula for the catchment efficiency for side feeding nozzle. It says the catchment efficiency equals to P naught square. We know the value of P naught. P naught is given to us 1 into 10 to the power 3 watt. Cos theta, theta is also given to us, and that is 60 degree. The angle between the powder feed nozzle and the vertical axis, that is 60 degree. Pi by 4 divided by 4 pi square dp, the diameter of the nozzle, and the nozzle diameter is given to us as 5 mm. Therefore, I can write it as 5 into 10 to the power minus 3 meter into K, that is given here 50 watt per meter Kelvin, into Tm minus T naught whole square. So I know Tm also and T naught as well. So after keeping all these parameters here, I will find that the catchment efficiency is coming around 10%. So this is typical catchment efficiency, even it is less than what I have predicted here in the case of the side feeding laser cladding press processes based on powder as a raw stock material. So with this, thank you very much.